Welcome back to Arts Physics Tutoring. In this video, we'll be going over range formula, as well as its derivation, and the only scenarios it works under, and some practice problems. As always, the more comprehensive problems will be on Arts. These are the more basic ones to make sure you have it in your memory, and you have it down right. Similar to the time of flight formula, this only works under one condition, this formula. The condition of leveled ground. That doesn't mean you're landing on ground. It just means that you start and you land in the same position. It doesn't look like this, or it doesn't look like this. It looks like this. Okay, so that's something you want to keep in mind. If it doesn't start and land in the same position, then you're going to have to use basic kinematic, and it's going to be a bit messy using basic kinematic equations. But this is the more general formula for leveled ground. Now, what even is range? Because time of flight is how long it stays, right? But you have to remember that this graph is the y motion graph. What does the x motion graph look like? How am I traveling as a function of x? So if you look at time, and then x distance, not y distance, x distance, then we know that this formula works, right? Xf is equal to xi plus vt, vxt. So this could be vx initial or vx final. It doesn't really matter, because for x, they're both the same, right? Because the velocity stays constant. So it looks more like a linear graph. And then plus vt, and the slope would be vx, which makes sense. So you see, the range is basically how far does it travel in the given time. So for your period, let's just say it's over here, okay, t. So your range is, when does your graph hit t, and what is the distance you covered at that point? What is your x distance? How far did you go in the x direction? So first, let me show you where we get our formula from, because as always, the goal of this channel is to provide you with everything, but most likely the how behind the why, and the why behind the how. I want to show you where we're getting this stuff from. So range comes out of the simple x position equation. Xf is equal to xi plus vt, vxt. This can be vxi or vxf. It doesn't really matter, because they're both the same. But for y, you know how this changes, right? vyf would be vyi minus gt, because it changes. But just look at this for now. So how do you get the range formula out of this? First, let me do delta x. So xf minus xi becomes delta x when we subtract on both sides. And here it just becomes vxit. Delta x that's exactly what we want, right? How far do you travel? Where did you start and how far did you travel? So delta x is our range. Considered only that this t is our final t, okay? Not just some regular t. Only if this t is our time of flight, or how long we stayed in the air. Then this is our ultimate range. Because if you pick any t, you can get multiple values, right? Range isn't constant if you do that. Range is only for your final t, or your time of flight, because once you're done with your flying duration is when you stop and when you have your full horizontal motion recorded. So vx initial times, big T. I'm just going to put in big T. So big T, you know what big T is, right? 2vi sine theta, because that's vyi, or in other terms, vi sine theta over g. Because vyi is just this, right? Because you just multiply by sine theta to get the other vector. And then vxi times that. So we know what v at psi is, which is just velocity initial times cosine theta. And then we have basically everything we need. So range is equal to x initial times t. Let me write that over here because I need some more space here. Now we can square the v squared. So it becomes 2vi squared over sine times sine theta times cosine theta over g. So I don't know whether you know this identity yet, but this is a fundamental trig identity, okay? Sine 2 theta is equal to 2 sine theta times cosine theta. So we're going to substitute that into this. And it's going to become 2vi squared sine theta cosine theta. We can just write that as vi squared times sine 2 theta over g. Notice how this vi doesn't have an x or a y, because we converted it at the start, right? We did vi sine theta instead of vyi. So now we're on the same term. This is just the magnitude of the velocity initial. No y direction, no x direction. So pretty neat, I'd say. This is your formula for range. You give it your angle, what's your angle, where you launched from, and then you give it your velocity initial. And the rest, it does by itself. So let's try a problem together. You launch at 22 meters per second. So velocity initial is 22 meters per second. Okay? At 35 degrees from level ground. So 35 degrees over here. Now this is an xy graph, okay? Not a ty or a tx graph. That's a bit different from these graphs, okay? xy graphs are different. xy graphs are just, how does your y change the function of x, which you can use parametric substitution for. I'm not going to go over that right now, but this is a different graph. Just keep that in mind. Here we have a x distance, not a t distance. And then find the range r using the formula. So the range r is over here because we start at 0. R is equal to velocity initial squared. So what is my velocity initial squared? 22 meters per second squared times sine of 2 theta, 2 times 35, over 9.81 meters per second squared. So it becomes, if you square the 22, 484 meters squared per second squared times sine of 70 degrees over 9.81. In other words, so this is meter per second squared as well. So you can understand the units become meters. 484 divided by 9.81. And that whole thing times sine of 70 degrees, which should get you around to 46.36 or 46.4 meters. So let's try a few more problems out. As always, pause the video and give it a try first before looking at me solve through them. Okay, let's go over them. Launches at 25 meters per second. So velocity initial. A projectile launches at 25 meters per second, 30 degrees from level ground. So we can use our range formula here. And find the range r. Velocity initial is 25 meters per second. And what else do we need? We need our angle. Theta is 30 degrees. So our range was going to be r equals vi squared times sine 2 theta over g. Or in other words, r is equal to 225. So let me show you where I got that from. 25 meters per second squared times sine of 60 degrees over 9.81 meters per second squared. So this should give you, if you square 25 squared, you get 625 times sine of 60. All of that divided by 9.81. you get approximately 55.17 meters. Always make sure you check the meters, because this could be feet or something, right? This case it's meters though, so you're good. Now, something I also wanted to mention is the fact that, so it's kind of irrelevant to this, but I didn't really find a good space to mention it earlier. If you launch a projectile at 30 degrees, you'll have a range. If you launch at 60 degrees, you'll have another range. Okay? But what projectile can you launch to have your maximum range? Sine 2 theta. Sine is exclusively between 0 and 1. Okay? So how do I get 1 from this? If I plug in 45 degrees here, sine 2 times 45 degrees will give me sine of 90. And sine of 90 will give me 1. That's why 45 degrees is the optimal firing for the projectile if you want the maximum range. That's going to get you over here if you fire at 45 degrees, because that's going to multiply by 1, while the others will be multiplying by 0 point something. You could have the same velocity initially as well. It just depends on what angle you fired it at, right? Now let's go over complementary angles. A 40-degree launch gives a range. Which other angle matches it? So before using formulas or anything, let's just go over the basics. Sine 2 theta is the formula used in the range, right? So this would become what? Sine of 80 degrees. Because this is what? It's 40 times 2. Now, if you draw your unit circles, and if you know them hard, like you should, then you know 80 degrees is over here. So what is parallel to 80 degrees, or an angle that is similar to 80 degrees, which gives me the exact same sine value? This one. Let me mirror it in pink. Because, you see, I mean, this might have a different cosine value, but that's not what matters, right? This one sine is positive, this one sine is positive. So, they're both the same. In the eyes of sine, at least. So what is the difference here? This is 80 degrees. To the y-axis, it's 10 degrees. Because y-axis is 90 degrees, right? And then from 90 degrees, you have to go another 10 degrees. Because you have to, these two angles will be equally distant from the y-axis. Equidistant. So 90 degrees plus 10 degrees is going to give you 100 degrees. But that's sine of 2 theta is equal to sine of 100, right? So 100 divided by 2 will give you 50 degrees, which is your answer. Both 40 degrees and 50 degrees will give you the same range, because when you multiply them by 2, they give you the same y values. So this is a rather new concept, right? Multiplying an angle by 2 and getting the same angles. So make sure you do brush up on these and your unit circle. Solve for the angle theta. Range is equal to 50 meters. So they gave this that. Speed is equal to 25 meters per second. Find theta. Take arc-sin and then half it. So that's just a hint. How I'd go about doing this problem is I write down the range equation first, before everything else. vᵢ² sin 2 theta over g. So r is equal to, I can say 25 meters per second squared. You might be like, well, velocity is not the same as sine, I mean speed, right? But the fact remains that this is the magnitude of the velocity. This isn't the direction. We don't care about the direction. We're just looking to see whether it has the same magnitude. And there's no VIX or VIY. That's part of the reason why this is so useful because it's just VI, no VIX or VIY. So VI, or the magnitude of the original initial velocity vector, is going to be the same as the speed. So 25 meter per second squared times sine of 2 theta over 9.81 meter per second squared is equal to, r is what? 50 meters. So if I multiply the 9.81 out in both sides, I get 490.5 meters squared per second squared is equal to, let me actually erase some of this to get more room. 490.5 meters squared per second squared is equal to 25 squared, 25 meter per second squared, times sine 2 theta. So 490.5 divided by 25 squared. And this is also going to give you units of meters squared per second squared. So the units here cancel out and you're just left with a value, which is what sine is, right? Sine doesn't have units. 490.5 divided by 625, arc sine of that. So I got 0.7848 is equal to sine of 2 theta. Take the arc sine of both of those, right? So you get arc sine of 0.7848. Then divide that by 2, because this is sine of 2 theta. And you get your answer of 25.85 degrees. And there you have it. So the other thing you need to remember is the domain for arc sine is only pi over 2, negative pi over 2, right? So this first half of the unit circle. But you have to remember that there's also this thing over here. So how do I get that? I have to manipulate this 25.85 degree angle to get that one. So if you know how we're going to do that, it's going to be over here, right? Because it has to be over here. It's 180 minus 25.85. So 180 minus 25.85, 154.15 degrees. That's the other angle that could be used. But that's going to send the projectile backward, which is pretty, not that often, is what I'm going to say, right? But this is the main answer. I just wanted to keep that one in mind for other circumstances. And in our next video, we'll be going over maximum height. Okay, so we know the range, we know the time of flight, but we don't know the maximum height a projectile can reach. And we're gonna know it, okay? So feel free to check my video out on that, and have a good day. Thank you for watching.